Factoring special products. Now that we've been factoring with a x squared plus bx plus c terms, where a is some number, or a is just 1, now we need to look at special products, because there are a couple different products or multiplications that are special circumstances which we can, if we recognize them, factor them following a pattern and use a shortcut on them. So the first one is where we have an x plus 1 squared, or any term where we have the same term factored or multiplied times itself. So if you look at these, we have x plus 1 squared, x plus 2 squared, x plus 3 squared. And if you look at what happens when we look at the FOIL part of this, we get x squared, and then outside is 1x plus 1x is the inside, plus 1 squared as the last term. Well, those middle terms are the same term, and so they add up to 2x. On the second one, the middle terms are 2x plus 2x, and they add up to 4x. So basically doubling 2x, doubling 1x. The middle terms here are going to be 3x and 3x, and when we double them or add them together, we get 6x. And so you can see that this first x is the square of the first term. This is doubling the second term times the first term, which is 3x, and the last one is the square of the last term. So we're actually taking the first and last in that middle one, the first and last term, and multiplying them together to get that middle term. So if you take that into account on this next one, you should have x squared as the first term. You should have 1 as the last term, because negative 1 times negative 1 is positive 1. And then we're going to take the first and the last term and multiply them by each other, so negative 1x, and we're going to times that by 2, so we get the negative 2x. And so same thing for negative 2, we're going to get x squared, we're going to get positive 4, and we're going to get a negative 2x times 2. And so they showed you the patterns out here, how that works. There's an x squared, there's a negative 2 squared, and then there's negative 2 times 2x. And if we can recognize this term, we can easily factor it. So the thing you have to remember is that you square the first term, you square the second term, and then you multiply the product of the first term and the second term by 2. So basically doubling it. And so this works with anything that you can recognize that pattern for. So if you look at this, 36 is a perfect square. That's 6, and 6 times 2 gives us the 12 that's here. So we know then that this is an x plus 6 times an x plus 6. So let's take a look at some problems here and determine whether they are perfect squares or not. So first thing is the first term a perfect square? Yes. Is the last term a perfect square? Yes. So we're going to have x plus 3 squared. And does that work out if we take the first term, first part of this, and the second part, 3 times x, and double it? Do we get 6x? Yes, so this does indeed work. So let's take a look at this next one. We have a perfect square here. We have a perfect square here. So that should be x. And since this is minus, we should have minus 2 here. And if we take x minus 2 squared, do we get this middle term? Well, negative 2x times 2 gives us negative 4x. So our middle term should have been a negative 4x, and it's not. So this one is not a perfect square. So we leave it just like that. Or we can try and factor it into 2 binomials. So let's see if it does factor into 2 binomials. And so if we look at factoring this as x, and 2 and 2, or 4 and 1, it says we're going to add those, and we're going to get a negative. So that means both of these would have to be negative. And so 2 plus 2 is 4, and 4 plus 1 is 5. There's no way that we're going to get a negative 2 in the middle there. So this does not factor. and so it is considered prime. Next one. So are the front and back term perfect squares? Yes, because 36x squared is 6x times 6x. And is 16 a perfect square? Yes, that's 4. And then let's, again, this is positive here, so we're going to add them, but a negative here, so this has to be a negative. And then let's check and see if that middle term worked. 6x times 4 is 24x, times 2 should be 48x. And do we get 48x in the middle? Yes, we do. And negative times negative is positive, but negative 48 plus negative, or negative 24 plus negative 24x will give us a negative 48x. So that is indeed a perfect square trinomial. Application. Here is this radio tower, and it says a cellular phone tower signal covers a circular area with a radius r in miles. The strength of the signal is increased, and now that covers an area of pi r squared plus 10 pi r plus 25 pi. The first thing you should always check on every problem is to see if there's something that can be factored out. What do all three terms have in common? They have a pi. So I'm going to take the pi out of that. And again, you do that by dividing it off. And so I get r squared plus 10r plus 25. And then I want to check and see if I can factor that. Well, I recognize 25 is a perfect square, so I should be able to factor that into something squared if the 10 is double the term at the end. So it's going to be pi, and then I know it should be r and 5. And plus, so positive here. And does that give me a 10r in the middle? Well, if I take 5 times r, and I times it by 2, yeah, that gives me the 10r in the middle. So I know that that is indeed a perfect square trinomial. Now, there's a second kind of pattern that we look for, and this one is called a difference of two squares. And what does difference mean? Well, difference means it's a subtraction. So it's a subtraction of two perfect squares. And so we're going to look at things like x squared minus 1. Can you take the square root of x squared? Can you take the square root of 1? Yes. And so since you can take the square root of both of those, then we can look at this pattern that happens. When we multiply those, remember we go x times x is x squared. And then we get the negative 1x and the positive 1x. And what happens to negative 1x and positive 1x is that they cancel out. And then we look at the negative 1 times 1, which is minus 1. And you could say that's 1 squared, because really 1 squared is still 1. And so that's how they got this x squared minus 1 squared. Now notice there's only two terms here when we get this down to something that we're going to factor. There's only two terms in this. So anytime you have just two terms or a binomial, you're going to look and see if it is a difference of squares. And again, it's a difference, so it has to be a subtraction problem, can't be an addition problem. So if you look at these, x squared minus 9, those are both perfect squares, so that's going to be an x minus 3 and an x plus 3. So let's take a look at a couple of these. 4x squared minus 25. Are those both perfect squares? 4x squared is 2x. Square root of 25 is 5. And it's going to be plus 5 and 2x minus 5. B. 9m to the 4th, is that a perfect square? Yes, because that's 3m squared. And 16n to the 6th is 4n to the 3rd. And so if you're not sure, multiply 4n to the 3rd times 4n to the 3rd. That's 16, and then you add the exponent, so n to the 6th. And again, if we have this working, it's going to be 1 plus and 1 minus. So 3m squared plus 4n squared. X squared minus 8. Is x squared a perfect square? Yes. That's x. Is 8 a perfect square? No, it's not. So if we don't have a perfect square, then this doesn't work. And if it's a binomial, in other words, two terms, and it's not a difference of squares, then we probably can't factor it. We might be able to factor something out of it, but we can't factor it. Now, notice what's different about D than the rest of them. The negative is in the front, and the positive is on the second term. So we want to flip this around so that it's a difference of squares, so that we're subtracting one from the other. So z to the 8th minus 64. And then are those both perfect squares? Well, z to the 4th times z to the 4th is z to the 8th, and the square root of 64 is 8, so plus and minus 8. Back here on C, again, we couldn't do anything with that if it was not a perfect square, so please make sure you're checking to see if those are perfect squares. Last one, example 4, is an application for a garden problem. It says Ganesh is designing a square border around a square pond. The area of the pond is 225 square feet. Use the difference of two squares to write an expression that represents the area of the border. So the first thing is that this is supposed to be a square. It doesn't look very square, but so it's 2f times 2f. If we know that, then we know that the area of the pond is 4f squared. I'm sorry, the area of the border is 4f squared. And we're going to subtract from that the area of the pond so we can figure out how big the border is here. So the 4f squared is the area of the whole piece. And so we're going to minus the area of the pond, which is 225 square feet. And so is 4f squared a perfect square? Yes, that's 2f. And this is going to be plus and minus since it's the difference of squares. Square root of 225 is 15. And so we have 2f plus 15 and 2f minus 15.